In a previous video, we modeled the dynamics of an age-structured population. That population was made up of juveniles and adults, and the demographic assumptions we made led to this recursive model for population growth. We saw that we could describe an explicit relationship between the age distribution and time by repeatedly applying the matrix from our recursive model to the initial age distribution. Specifically, we could get the age distribution in year t by applying our matrix to the initial age distribution exactly t times. While this approach to calculating the age distribution at time t does lead us to the kind of prediction we might want to make, it's not very practicable, especially if we're looking to predict the age distribution several years into the future. Imagine, for instance, how tedious it would be to generate the predictions about the age distribution just 10 years into the future. As it stands, to arrive at these predictions would require us to carry out 10 separate matrix vector multiplications. Thankfully, there's a better way to make projections about age-structured populations. This better way relies on eigenvalues and eigenvectors, and the goal of this video is to lay out the steps involved in doing this. The first step in developing a practicable model for predicting the age distribution is to find the eigenvalues of the matrix at the center of the recursive model. Remember, to find eigenvalues, we subtract lambda from the diagonal entries of the given matrix, calculate the determinant of the result, set that determinant equal to 0, and then solve for lambda. Given the numbers we're working with, we find that the eigenvalues of the matrix are 2 divided by 5 plus the square root of 19 divided by 5, and 2 divided by 5 minus the square root of 19 divided by 5. Our second step is to find eigenvectors associated with each eigenvalue. In this example, finding the eigenvectors is a rather simple task. Recall that an eigenvector v associated with an eigenvalue lambda satisfies this equation, which can be rewritten as follows. We know that there's not just one unique solution to the system of equations, a fact that means we can choose the value taken by the first entry of the eigenvector v. With that in mind, we focus on this, which tells us that if we choose to set v1 equal to 2, then v2 must be equal to lambda. Overall, that means this is an eigenvector associated with our first eigenvalue, and this is an eigenvector associated with our second eigenvalue. Our next order of business is to express the initial age distribution as a linear combination of the eigenvectors we just identified. Mathematically, that means finding constants a and b such that a times one eigenvector plus b times the other eigenvector is equal to the vector x1 at 0, x2 at 0. To keep our discussion more concrete, let's say we've been told that initially the population consisted of 10 juveniles and 2 adults. To find the constants a and b, we turn the vector statement before us into a system of two linear equations. Equation 1 and equation 2. From equation 1, we get b is equal to 5 minus a. Now, we sub this into equation 2 to get this, which can be simplified to give us this. It follows that in this particular example, the constants a and b are both 5 over 2, and so our initial age distribution can be written out in terms of the eigenvectors we identified as follows. We're now ready to turn this rather cumbersome version of our model into something more usable. Keep in mind that we're working with an initial age distribution captured by the vector 10 and 2. Also, keep in mind that the initial age distribution can be written like this. Substituting this into our cumbersome model, we arrive here. If I now bring the rightmost copy of the matrix inside the brackets, I get this. Notice that I've got t minus 1 copies of the matrix outside of the brackets. Notice also that the two matrix vector multiplications inside the brackets are dead easy to pull off. Because they both involve eigenvectors, we can replace the matrix with its appropriate eigenvalue to get the following. We can repeat the procedure by bringing another copy of the matrix inside the brackets. When we do this, we leave t minus 2 copies of the matrix behind. But again, we have matrix vector multiplications inside the brackets that are easy to compute. They're easy because the vectors involved are eigenvectors of the matrix, so we can just replace the matrix vector multiplication with multiplication by an eigenvalue. If we tidy this up a bit, a pattern starts to emerge. We see that we've peeled off 2 copies of the matrix from outside the brackets and have been able to replace them with multiplication by eigenvalues raised to the power 2. If we keep repeating what we've been doing, we will have eventually peeled off all of the t original copies of the matrix and replace them in aggregate with multiplication by eigenvalues raised to the power t. Overall, what we're left with is a really useful formula for the age distribution as a function of t. If we were now asked to predict the number of juveniles and adults respectively 10 years into the future, we could do so with relatively little computational effort. At this point, it's worth looking at the general structure of the model we've come up with. Essentially, we have one eigenvalue raised to the power t multiplied by its eigenvector. We have the other eigenvalue also raised to the power t and also multiplied by its eigenvector. And we've expressed the age distribution at time t as a linear combination of these eigenvalue-eigenvector products, where the constants involved were determined by the initial state of the age-structured population. Let's recap. Our goal in this video was to devise a practicable version of a model for the relationship between the age distribution in a population and time. We found this version of the model by doing 3 things. First, we found the eigenvalues and eigenvectors of the matrix connected to our recursive model for population growth. Second, we expressed the initial distribution as a linear combination of the eigenvectors that we found. Finally, we used the combination of eigenvectors to replace repeated applications of the matrix with repeated multiplication by an eigenvalue. By the time you've wrapped your head around the ideas presented in this video, you won't have acquired a new ability per se. However, you will have refined the abilities you have quite substantially. You'll be able to establish models for the relationship between the age distribution in a population and time, like you were able to do before. But now, your models will be much more convenient from a computational perspective. I want to add here that the skill you acquire does not have to be applied to model the growth of age-structured populations only. Indeed, you should be able to go beyond age-structured models of population growth and derive predictions arising from other linear models of biological phenomena. That said, it should be evident that watching this video is only the first step toward building your ability to apply eigenvalues and eigenvectors in biological modeling. Try to imagine other scenarios where the ideas you encountered here might be of use. And don't be afraid to share your ideas with others. As always, the course notes are meant to be read, so read the relevant sections. The assigned problems are meant to challenge you, so try them too. Stay consistent, and you'll position yourself to succeed.